All right, so hi everyone. In this video, we're gonna kind of take on our next section here where we're going to learn about integrating some more complicated functions using something called substitution. So let's take a look here at a couple quick warm-up examples. In this first problem, we get derivative of sine of 4x. Well, we know the derivative of sine is cosine, so we'd have cosine of 4x. But because of the chain rule, I know I have to multiply by 4. So my answer there is 4 cosine of 4x. Well, if I do the integral in number 2 of 4 cosine 4x, I know I'm trying to do the antiderivative. Well, the antiderivative of that answer we just got should be sine of 4x. So this equals sine of 4x plus c. Well, what happened to the 4? So we had this 4 that seems to have disappeared in our answer. Well, where did it come from in number 1? It came from chain rule. So it's kind of like we undid chain rule, because for the antiderivative of cosine of 4x times 4, I went backwards to sine. That's similar to like our antiderivative rule. But then because this 4x would have had chain rule giving us that 4, we have to undo it. So it's like we divided by 4. So if we did an example like number 3, where there was no 4 coefficient, I would have here that the antiderivative of cosine is sine, so sine of 4x, but I have to undo chain rule, so I have to divide it by 4. So I really have 1/4 sine of 4x, or sine of 4x over 4, plus c. So it's starting to try to see a little pattern here of if I have a coefficient on the inside where like chain rule would have done something with that, I have to undo that chain rule. Let's look at a few others. So here we have the derivative of e to the 1/3 x. So I know the answer to that would be itself, e to the 1/3 x times 1/3 by chain rule. So 1/3 e to the 1/3 x. And so in number 5, if I did the antiderivative of that, it should go back to the original. So I would have the antiderivative of 1/3 e to the 1/3 x would just be e to the 1/3 x plus c. Where did the 1/3 go? Well, we had to undo it. So kind of dividing by 1/3, which is really multiplying by 3. So for number 6, that would give me the antiderivative of e to the 1/3 x. Now I don't have that original 1/3 coefficient. It's still going to be itself. The antiderivative rule for e to the x is just itself. But since I got that 1/3 coefficient, I have to undo chain rule. So instead of dividing by 1/3, I would multiply by 3. By meaning just multiplying by the reciprocal there, plus c. So this leads us to kind of an idea of using substitution to help us with more complicated versions of this. And so if we look at that kind of formula we had for chain rule, the derivative rule, derivative of a composition, f of g of x, is f prime, so the derivative of the outside at the inside, f prime of g of x times g prime of x. That means we could go backwards. We could say that the integral of f prime of g of x times g prime of x dx would equal that original f of g of x plus c. And so the key thing that we're really going to focus on is this idea of there's sort of an inside function like g of x, and its derivative is hanging out on the outside here, g prime of x. We're going to look for that in these next couple problems. All right, example 1. Copy it down here. The integral of x squared plus 1 quantity squared times 2x dx. all those steps on the right side, maybe you could write them down after we do this equation, or this problem, up to you, or before. Pause the video whenever you're going to do that. But here's what we're kind of looking for. So what I notice is I've got this kind of stuff squared times 2x. And if I look at that stuff that inside x squared plus 1, what's its derivative? It's 2x. And hey, I recognize that out there. So when you get to this situation, what we do is we set the inside equal to u. So we do some side notes here. We say u equals x squared plus 1. And then I'm going to take the derivative of it. Du dx equals 2x. Okay, now what we do is, remember back a couple sections ago, we did differentials, and we kind of moved the dx over to the other side. So du equals 2x dx. And so what we need to notice here, I have u is the x squared plus 1, and this du is 2x dx, which I have in that integral 2x dx. So now I'm going to make this substitution. And so this problem is going to be rewritten as the integral of u squared, x squared plus 1 is u, so u squared, and then 2x dx is du. Oh, look how much easier that integral is. We know how to do that one. The integral of u squared is u cubed over 3 plus c. And then I'm going to sub back in for u, because I need my original problem there. It's going to be x squared plus 1 to the third over 3 plus c. And that's how we do u substitution. So you get, like, those steps here are what we just did. So pause it, write those down if you haven't yet, and then we'll do a couple more examples. All right, example 2. Again, we're kind of looking for this idea of some inside function and then its derivative, or a version of it, written on the outside. So here I have on the inside 2x cubed plus 5, and its derivative is 6x squared. Well, this says 3x squared, but that's pretty close. It's x squared. That's what's going to be the most important, that it's kind of the same level. It's the same degree or type of function. So here I'm going to go u equals the inside, 2x cubed plus 5, and then I take the derivative. Du dx equals 6x, and I move the dx over. Du equals 6x dx. Now as we get to doing these more and more, we always move the dx over, so you can kind of just go straight to du equals 6x dx. Okay, now, 6x squared. Sorry, let's fix that. 6x squared, 6x squared. So then, what I notice here, okay, I'm going to plug in, I've got the square root of u, but what's left over right now is still 3x squared dx. And I have 6x squared dx. I need to make them look the same. So in order to get that 3, I have to divide this by 2 on both sides. I go divide that by 2, divide that by 2. So now it's 1/2 du equals 3x squared dx. And now I can make that substitution. I have to get all the pieces there to substitute out. So this will be right as the integral of square root of u, and then the 3x squared dx is times 1/2 du. Okay, I can pull that 1/2 out in front, and I can rewrite square root of u. So 1/2 integral of u to the 1/2 du. So this will be 1/2, and then I would add 1, so u to the 3/2 divided by 3/2, or times 2/3. So I have to multiply there, plus c. And that's going to give me, I got the 2's canceling, so 1/3. And then I should plug back in for u. U was 2x cubed plus 5 to the 3/2 plus c, or you could write that in radical form as well. Okay, 2 more. Let's go here, and we're going to notice that maybe we should rewrite this because I got that sine squared. So I want to be able to visualize that better. This is sine of 3x squared times cosine of 3x dx. And my inside there now is sine of 3x. The derivative of sine is cosine. It's on the outside. Perfect. I have that situation that I like. So now I can set up my u substitution. U is going to be the inside, so sine of 3x. And then du will be derivative of sine is cosine of 3x times 3, because of chain rule, dx. Right? I moved the dx over right away instead of writing it. Okay, so I only want to see cosine 3x dx. So I got to move that 3 to the other side. So I can divide by 3. So it'll be 1/3 du equals cos 3x dx. And now I can sub in. So it's going to be integral of u squared. Sine of 3x is u. Cosine 3x dx is 1/3 du. So I have the du, and I can right away bring the 1/3 in front. 1/3 u cubed over 3 plus c equals, and then I'll plug back in sine of 3x, so this would be sine of 3x cubed over 9 plus c. All right, last one. If you think you want to try it on your own, pause the video. What I notice here, so I've got e to the something, and then multiplied outside here. So like my only inside is the exponent of e, tan x. So let's see if this sets up correctly. We've got u equals tan x, and we just try it out. What's du? That would be derivative of tangent is secant squared of x dx. Great. That's going to work out, because now when I see secant squared x dx, I can plug that in. So we get the integral of e to the u du. E to the tan x is u, so e to the u. Secant squared x dx is du. Well, integral of e to the u is itself plus c, and so then I just get e to the tan x plus c. All right, that should be a good start for tonight's assignment. Thanks for watching.